All right, if you're gearing up for your STPM exams, you know integration is a huge deal in calculus. But have you ever stopped to think about what it's actually for? It's not just a bunch of symbols on a page, you know. It's like a mathematical superpower for measuring all sorts of complex, curvy shapes in the real world. So in the next few minutes, we're going to master two of its most powerful uses, finding area and volume.
So here's the game plan. We'll kick things off with the big idea of what integration even is. Then we'll use it to nail down the area under a curve, and then the area between two curves. After that, we're going to make a huge leap from the flat 2D page into 3D space to figure out volume. And we'll wrap it all up with a quick fire recap of the key formulas you're absolutely going to need for your exams.
So what's the big deal with integration anyway? Well, at its heart, it's actually a beautifully simple idea. It's all about adding things up. But not just any old things. We're talking about infinitely small things.
I mean, think about it, right? We've got formulas for squares and triangles, all those nice shapes with straight edges. But what about a space that's boxed in by a smooth, flowing curve like this one? How on earth can we find its exact area? This is where the real magic of calculus kicks in. Just imagine slicing that area under the curve into millions and millions of paper-thin rectangles. Now, we can usually find the area of any one of those rectangles. Well, integration is just the process of adding up the areas of all of those infinitely tiny rectangles to get the perfect exact total. It's how we handle the infinite. Okay, let's put this idea to work. We're going to start with our first practical application, finding the area that's trapped between a curve and the x-axis.
This formula right here, this is your key. That long S shape is the integral sign, and it basically just means sum it all up. So we're summing up the function's height, which is f of x, across all these tiny little widths, from our starting point A to our end point B. And as you can see in the animation, what you get is the precise shaded area under that curve. Now listen up, because this is a classic exam trap. If your curve happens to dip below the x-axis, the integral will actually spit out a negative number. But wait, can you have negative physical area? Of course not. So here's the crucial thing to remember. If you're asked for the total area, you have to take the absolute value of that negative answer to make it positive.
Okay, so we've mastered the area under one curve. But what if you've got two curves, and you need to find the area of that region that's locked between them? This is a super common question, so let's break it down.
The logic here is actually surprisingly simple. The first thing we do, as you can see, is just calculate the entire area under the top curve, f of x, all the way down to the axis.
Next up, we do the exact same thing for the lower curve, g of x. Now watch what happens when we take that lower area and subtract it from the total upper area. What do you think is left behind?
Exactly. We're left with just the area that's trapped between them. And this gives us a brilliant way to see the formula. You simply integrate the top function minus the bottom function. It really is that straightforward. And now for the really amazing part. So far, we've been working in a flat, 2D world of areas. But with one simple twist, integration can launch us right into the third dimension, volume.
Take that same 2D area we just calculated. Now imagine grabbing it and spinning it a full 360 degrees around the x-axis, just like this. As it rotates, it carves out a solid three-dimensional shape. This thing is called a solid of revolution, and believe it or not, we can find its exact volume.
So how in the world do we measure the volume of this new complex shape? Well, we use a technique called the disk method, and it uses the same core idea we started with, slicing things up.
Here's how it works. Look at step 1. We start with just one of our original super thin rectangles. In step 2, we rotate only that one rectangle and it forms a thin disk, kind of like a coin. Now we know the volume of any disk is pi times the radius squared times the height. For our little disk, the radius is just the height of the curve, f of x, and the height of the disk is that tiny width, dx. So to get the total volume, we just integrate to sum up the volumes of all the infinite disks that build our final shape. It's brilliant.
And this leads us straight to the formula. The volume is pi times the integral of your function squared. So why is it squared? Because f of x is the radius, and the formula for the disk's volume needs radius squared. That little square is the key difference you have to remember when you're calculating volume. And just so you're prepared, you can also rotate around the y-axis. The concept is exactly the same, but your formula just changes a little bit. You'll integrate with respect to y, and the function has to be written in terms of y, so you'll be using x squared inside that integral.
Phew, we've covered a lot of ground. moving from 2D planes all the way to 3D solids. So let's put everything side by side in a simple table. This next slide is absolutely perfect for your exam revision notes.
This table lays it all out nice and clear. For area, you just integrate the function. For the area between curves, you integrate the difference of the functions. And for volume, the two crucial changes are you multiply by pi and you square the function. If you can memorize these key differences, you're going to nail these questions on your exam.
And we'll end with this thought. You now have the mathematical tools to actually define and measure complex 3D shapes. So look around you, a vase, a bottle, maybe a lampshade. Start thinking about the 2D curves that you could rotate to generate those shapes. This isn't just abstract math. It's a whole new way of seeing the geometry of the world. Good luck with your studies.